Look closely at these expanding geometric archways. When numbers scale infinitely into space, human intuition starts to break down. If I show you a list of numbers, say 2, 5, 10, and 17, you might be able to guess the next term. But what if I ask you for the 100th term, or the 1000th? You simply do not need to guess. There is a precise, step-by-step mathematical system that allows us to decode the underlying rule of any pattern. By moving away from visual estimation and relying on algebraic proof, we can accurately predict the exact value of a sequence at any point in the deep future. Let's start with step 1, using a simple, steadily growing sequence. Take the numbers 5, 8, 11, and 14. We run what we call the difference test. We map the rate of change by strictly subtracting the previous term from the current term, meaning we work right to left. 8 minus 5 is 3. 11 minus 8 is 3. 14 minus 11 is 3. This strict order prevents calculation errors. Notice the results beneath the arcs. The test gives us a perfectly constant baseline where every single difference is exactly 3. When a sequence has a constant first difference like this, we classify it as an arithmetic sequence. Finding a constant number on this very first layer means the structural code of the pattern is solved. We know exactly how it behaves. Now let's test a sequence that accelerates. 2, 5, 10, and 17. We apply our subtraction test again. 5 minus 2 is 3, 10 minus 5 is 5, 17 minus 10 is 7. The first layer of differences is constantly changing. Instead of stopping, we move to step 2 and dig deeper. We run the exact same subtraction test on the first differences we just found. 5 minus 3 is 2, and 7 minus 5 is 2. Down here on the second layer, a hidden constant number emerges. This multi-layered structure with a constant second difference is the definition of a quadratic sequence. So a changing first difference is not a dead end. It is the mathematical signature indicating you need to test for a deeper quadratic pattern. Now that we have mapped both layers, we can use them to calculate the next unknown number in the sequence. We use a bottom-up addition method. Take our constant second difference of 2 and add it to the final first difference, the 7. That generates a 9. Next, we bridge that new 9 up to the base sequence, adding it to the 17. Our next term is 26. By charting the hidden architectural layers of the problem, predicting the immediate next step becomes an exercise in basic addition. Finding the very next number is helpful, but calculating the 100th term manually would take far too long. We need a way to bypass the intermediate steps entirely. For an arithmetic sequence, the general formula is Tn equals A plus n minus 1 times d. Applying this to the sequence 4, 7, 10, 13, A represents the first term, 4, and d is our common difference, 3. Now we simplify. We distribute that difference of 3 into the parentheses. Be careful with your signs here. That gives us Tn equals 4 plus 3n minus 3. Combining the numbers, we arrive at our final rule. Tn equals 3n plus 1. We can run a quick sanity check to verify this. If we plug in 2 for n to find the second term, we get 3 times 2 plus 1, which equals 7. The formula works. Building this master equation turns a simple list of numbers into an instantly solvable mathematical law. This diagram shows a top-down view of theater seating. The physical expansion follows a strict pattern. Row 1 has 20 seats, row 2 has 24, and row 3 has 28. We map these physical dimensions directly to our arithmetic formula. Our starting term, A, is 20. Our common difference, D, is 4 seats per row. So our formula becomes Tn equals 20 plus n minus 1 times 4, which simplifies down to 4n plus 16. If we need to know the exact capacity of the 15th row, we plug 15 in for n. 4 times 15 is 60, plus 16 gives us exactly 76 seats in that distant row. Mastering these linear patterns gives you absolute predictive control over physical scaling. Next, we will step up and learn how to build formulas for the even more complex, multi-layered quadratic sequences.